My name is Diego Lefebre. This is Statistical Analysis BA 642, Section 1, the final exam free response. The first case that we're going to look at is Part Inc. They initially wanted to to test whether the new ball had the same or better distance in terms of the coverage that the ball was going to get. So with that, we started a two sample t-test to differentiate between the means, and that would give us an appropriate estimate as to if the new coating would give a better effect on the golf ball or make it worse. Initially, we wouldn't want the ball to be worse as it's supposed to be an improving and better product. Therefore, we tried two different hypotheses, one with a new mean and the other one with not the other one with an alternative hypothesis. Therefore, we got a t-statistic of negative 1.328 and a p-value of 0.188. Since the p-value is greater than the initial hypothesis, we failed to reject that there's a significant change in terms of the coding and how that affects the ball and its performance. Because there's not enough evidence in terms of how many of the sample size. The sample size was about 40 shoot 40 shootings or 40 tests of the ball. We got a mean yardage of 270 with the current ball and the new ball 267.5. Therefore, just not enough of a difference to completely say that the new ball is significantly better than the old one. Um, Therefore, we reject the hypothesis that is better, and we state that the ball is not better, but neither worse. The confidence interval includes 0. There's difference not statistically significant. The new ball may be slightly shorter, the same, or even slightly longer than the current model in the population. To have a more accurate estimate if the ball is better, we would need a bigger sample size to have a more accurate answer to it. For Chapter 12, Case Problem 1, a bipartisan agenda for change. For this specific case, we were looking at understanding if certain actions and reforms were based on a very partisan basis. If for a certain law that was going to pass, a Democrat or the Independent or Republican Party member would say yes or no. So we wanted to differentiate between what was the correlation between the answers and the groups that it resembled to. Republicans showed the strongest support. Democrats and Independents show support, but the pattern differs by party. There appears to be some relationship between the party and the response. Question one, we got it. We tested a chi-square test of independence for question one, with the degrees of freedom of 2 and a p result of 0.0061. Because the p value is less than 0.05, the null hypothesis of independence is rejected. We continue testing with chi-squares and testing a hypothesis, and the results indicate that it brought bipartisan support for 2 or 3 reforms. Therefore, there is a significant change in how people answer depending on what their political views or affiliations are. So with chi-squares testing, we found that there is a correlation between the answers and the party that they feel resonates with them. Chapter 12, Case Problem 2, Fuentes Salty Snacks Inc. This case evaluates whether Fuentes candied bacon potato chips have consistent grocery store penetration. So initially, we wanted to see how how many of the stores in different regions carry the product and what the distribution that is. With that, we did a chi-square test for to test a hypothesis to see um the penetration of Fuente Salty snacks. Um, with that, we wanted to see if it's the right distribution, if there's better stores to have the product in and have more success. So we laid out using descriptive statistics, the regions, the stores carrying the products, and the proportion of that of the distribution of the product. With the chi-square test, we found that the null hypothesis of equal penetration rejects rate is rejected. Um, the hypothesis test support evidence that penetration of Fuentes candy bacon potato chips in grocery stores first across its 8 U.S. sales regions. We found that regions for Fuentes candy bacon potato chips lower or higher than expected. We used a Marskulu pair with comparison procedure at a 0.05 test to different between regions. We found that the Pacific region has significantly lower penetration than the Great Plains and Deep South regions. Therefore, with that, we can make an educated assumption that the distribution should be changed to the regions that is facing more success to have a more profitable product. Chapter 14, Case Problem 2, the Use Department of Transportation. This case examines whether cities with higher percentage of licensed drivers under the age of 21 experience higher fatal accident rates. Using data from 42 cities, the analysis evaluates the relationship between young driver prevalence and fatal accidents per 1,000 licenses to inform transportation safety policy. With the script analysis summary, we found that there is a positive correlation between only the age of 21 and number of fatal accidents for 1,000 licensed drivers over a 1 year period. Numerically, the percentage of drivers under 21 ranges approximately from 18 to 18%, while the fatal accidents for 1,000 licenses range near 0 to just above 4. The mean percentage of drivers under 21 is in the low to mid-teens, and the mean fatal accident rate is slightly above 2 accidents per 1,000 licenses, indicating moderately variability across cities. A scatter plot was used to analyze this distribution and this correlation, again, to have a better understanding of the age gap and how many accidents happen per 1,000 licenses. With that, we found that there's no extreme outliers, and the service cities with higher percentage of under 21 drivers also exhibit some of the highest accident rates, reinforcing the observed trend. We found that there is a noticeable upward trend. Cities with a higher proportion of young drivers tend to experience higher fatal accident rates. While there is some dispersion in the data, the overall pattern suggests a positive association rather than a random distribution. We use a regression analysis to investigate the relationship between the number of fatal accidents and the percentage of drivers under the age of 21. To formally investigate this, we did a simple linear regression conducted for fatal accidents for 1,000 licenses as a dependent variable percentage. The estimated regression model shows a positive slope, indicating that as the percentage of young drivers increases, the expected number of fatal accidents also increases. The regression results suggest that each of 1 percentage point of increase in drivers under 21, the fatal accident rate rises by a measurable amount on average. Overall, the regression analysis supports the conclusion that the percentage of licensed drivers under the age of 21 is a significant predictor of fatal accident rates across cities. We can recommend that based on both numerical summaries and regression analysis, there's clear evidence of positive relationship between the percentage of drivers under the age of 21 and the number of fatal accidents per 1,000 driver's licenses. We recommend strengthening graduate driver license excellence programs, increasing driver education requirements, and implementing stricter enforcement of speed limits and impaired driving laws for younger populations. Additionally, public awareness campaigns focused on risk reduction among drink drivers may help mitigate accident rates. For Chapter 15, Case Problem 1, Consumer Research, Inc. This case analyzes data from 50 consumers to determine how annual income and household size can be used to predict annual credit card charges. Using descriptive statistics and regression analysis, the study evaluates the strength of each variable as a predictor of development in the model to estimate expected credit card spending. The sample consists of 50 consumers. Annual income ranges from approximately 21,000 to 67,000 household size ranges from 1 to 7 individuals, and annual credit card charges vary substantially across consumers. The descriptive statistics indicate moderate variability in income and household size. While credit card charges exhibit great dispersion, the variability suggests the consumer spending behavior differs meaningfully across households and support the use of regression analysis to explain the credit card charges. A linear regression model was used to estimate use using annual income as an independent variable. The result shows a positive and statistically significant relationship between income and annual credit charges, indicating that higher income consumers tend to charge more on their credit cards. For household size, we showed positive relationship with annual credit card charges, suggesting that larger households incur higher spending. Comparing the two models, annual income is a better predictor of the annual credit card charges because it explains the larger portion of the variation in spending and exhibits stronger statistical significance than household size alone. A multiple regression model was used to develop both annual and income household size and its independent variables. The estimated regression pretty shows both variables have positive coefficients and contribute meaningfully to explaining annual credit card charges. Using the multiple regression equation, the predicted annual credit card charge for a 3-person household with annual income of $40,000 is approximately $3,230. This estimate reflects the combined effect of income and household size and expected credit card changing spending. Although income and household size are useful predictors, additional variables could improve the model's explanatory power. Potential variables include age, marital status, education level, and number of credit cards held. Ownership status and debt-to-income ratio include behavioral and demographic factors will likely improve more comprehensive understanding of consumers' credit card and spending patterns. With this, we conclude the presentation of the final exam free response. I will also be including the the charts and the analysis done on Excel to better illustrate the points and the work shown to get to these answers. Thank you.